We're going to start with an introduction to linear algebra, essentially talking about the different things that we're going to cover and some of the basic definitions we need to get started. And so I want to give you an idea of how we're going to proceed, because this is actually going to be similar to how we do the section on probability. We're going to start off with some basics, and this will be things that you pretty much already know, but we're going to look at it in a little closer detail. So first we're going to start off looking at how to solve the linear equation ax is equal to b. We're going to talk a great deal about Gaussian elimination, which is something that all of you know very well. But we're going to talk about another method, which is the way that people actually solve linear equations numerically, LU decomposition. And then we're going to talk briefly about QR decomposition. This is a technique we use for special types of linear systems, especially those that occur in statistics a great deal. And we're going to talk about those more in the second week, because they require a little more theoretical basis for us to really understand well. What's really important are the properties of the solutions for linear systems. And we're going to cover 4 basic theorems that are going to be very useful and that you want to memorize and understand how to prove. So once we've pretty much covered this, then we want to go back and we want to look at matrices in general. And we're going to talk about the 3 major operations we can do on matrices, which are transposes, inverses, and determinants. Okay, we're going to cover transposes and inverses in great detail. Determinants are a little more difficult to really understand well, so we're going to hit the highlights but not go into a lot of detailed proofs. And the last thing I want to cover are eigenvectors and eigenvalues. And so we're going to talk about what they are, how to compute them. This is something that for large matrices most people don't know how to do, and some of the applications. And if we have some time, either this week or next week, we'll talk about something called generalized eigenvalues also. Well, next week we're going to go on and talk about more advanced topics, and the first thing we're going to do is we're going to look at linear algebra from an abstract point of view. So we're going to consider matrices and vectors as being operators and objects that are in what we call vector space. And so these are terms that I'm sure you've heard, but we want to understand what they mean very well, and we're also going to prove some very basic theorems that we're going to use a lot. So once we have this theoretical foundation, then we're going to go back and we're going to look at the solutions of linear systems in a more theoretical way. So we're going to talk about the 4 fundamental subspaces of a matrix and what they tell us about the solutions. And finally, we're going to cover a very important theorem known as the rank plus nullity theorem. Now once we know all of this, then we're able to start talking about advanced techniques. So then we're going to talk about QR decomposition, Gram-Schmidt orthogonalization to create orthonormal bases. And once we've understood eigenvectors and eigenvalues, we can go on and we can talk about similarity transformations, singular value decompositions. And also, once we understand QR decomposition, then we can talk about pseudo-inverses. And if we have some time, we'll talk about some applications like principal component analysis applied to covariance matrices and things of that sort. What I want to do in the rest of this video is just very briefly talk about linear systems. So we say that we have a linear equations and n variables, and it turns out there's 2 different ways we can write this. We can represent it algebraically and we can represent it geometrically. Okay, so most things in math have this kind of duality, okay, between algebra and geometry. And the algebraic representation just says if we have n variables that satisfy an equation of this form, then this is called a linear equation and n variables. So you notice the condition is that each term has to contain at most 1 variable, and it has to be linear in that variable. Okay? Now the geometric representation basically says that if we have some point in an n-dimensional space that satisfies a linear equation and n variables, this is true if and only if those points all lie on the plane in some Euclidean n-dimensional space. So this is what a linear equation is. Now if we want to talk about more than one linear equation, because usually just knowing that these points lie in a plane doesn't really tell us a great deal. We're usually interested in satisfying a bunch of linear equations at the same time, all in the same variable. So we say that we have a linear system of equations in n variables if we have any finite number of linear equations all in the same n variables. So they look like this. So this is a case where I have m linear equations in the n unknowns. Okay. Now we're going to go back and write this in a matrix form. All right. Where of course x is the n component vector, b is the right hand side. Okay, it's an m component vector, and a is the coefficient matrix. It's an m by n matrix. Now there's a little bit of notation we're going to use. Sometimes we're going to want to talk about the ith row of A, and we're going to use the following notation. We're going to bracket A and then put an I with a dot after it. Okay. And sometimes we want to talk about the jth column of A. We can use a similar notation. And the last specialized notation we're going to want to talk about is that for the identity matrix. So the n by n identity matrix will be represented as follows. I will try as much as possible to be consistent in my usage of a boldface lowercase letter with an arrow meaning a vector, and a capital letter with a double underline to mean a matrix. The double underline is kind of old-fashioned notation, but I think it's good to be clear as to what we're talking about. Okay. All right, that's all for the introduction. Now we're going to go on and talk about solving the linear system AX is equal to B.